So now we know what kind of an animal we're looking for. We're looking for a strategy profile, that is a pair, which consists of strategy of player one, which is an infinite sequence of C's and S's, and a strategy for player two, which similarly is an infinite sequence of C's and S's. Okay. So, how do we find it? Again, the key thing is okay, so that's what we're doing. So we said when delta is equal to 1, even though the game is not meaningful, and the reason why the game was not meaningful was because we could not assign a payoff to, well, not that we could not assign, we did not assign a payoff to the infinite history, okay? But one observation, even though it was not a meaningful game in that case, one observation that you made was any subgame of the game is, I'll use in quotations, identical to the original game. Identical, exactly the same if the subgame starts by an action of player one, and it will be the same game as the original game if we take a game in which player two starts, but rename player two and player one. Name player two as player one and player one as player two. Okay? Any questions? Now, what if, of course, delta cannot be equal to 1 because, as we said, it's not meaningful.
Well, it still works because every utility is multiplied by the same constant, so it's still the same preference.
Exactly. That's the key. Okay? Even if delta is not equal to 1, this game, and this game are identical. The preference relations are the same. Okay? When player one compares this history and this history, the preference relation, okay, if 1 is bigger than 2, is bigger than delta 2, okay, that is if he prefers this history to this history, then delta square would be bigger than, delta squared times 1 will be bigger than delta cubed times 2. He would prefer this history to this terminal history. Okay? Okay? Actually, take this subgame, divide all the payoffs by delta square, you'll get this one. Okay? And we know that preference numeric representations were, I'll say, invariant under monotonic transformation. Delta is positive, so that will work. Okay? So, even when delta is less than 1, what you have observed is still true. Okay? This subgame and this subgame are the same. This subgame in which player 2 starts and this subgame in which player 1 starts is the same given the renaming. Okay? Okay? Of course, this only works when delta is positive. When delta is equal to 0, this game and this subgame are not the same. Okay? So far, so good? So that's something we would use. So we need delta to be between 0 and 1. We need it to be less than 1 for the specification to be complete. We need it greater than 0 so that we can use this. Every subgame is identical to the original game. Okay? And that's what we're going to be using. And actually, this is a technique that's useful in games of this form. So, what to do? Given this observation, what to do? Well, first of all, I don't even know whether there is a subgame or not. Okay? So, but if this game had, I don't even know if there is a subgame perfect Nash solution or not. I know that there is a subgame. I don't know whether there's a subgame perfect Nash solution or not. But if there was, if the set of subgame perfect Nash solutions was not empty, okay, when player 1 takes the action G at this information set, what is the maximum payoff that he can expect at any subgame perfect Nash solution of this subgame? It's 2 or so if player 2 says stop, his payoff is going to be 2 delta. If he says go and then player 1 says stop, it's going to be delta square 1. If he says go and then stop, it's going to be delta cube 2. Okay? So subgame perfect Nash or not, no matter how the players play the subgame, what is the maximum payoff that player 1 can get when he says go? It's going to be 2 delta, right? So if he says go, the maximum payoff, whatever the players play in this subgame, is going to be 2 delta. So if 1 is bigger than 2 delta, what would you expect player 1 to do? Stop here, right? Because if he says go, maximum payoff for player is 2 delta. If he says stop, his payoff is 1. So if 1 is greater than 2 delta, or delta is less than 1 over 2, player 1 will take the action G at the initial, I'm sorry, not G, S at the initial okay. So far so good? So far so good? Well, what about player 2? Well, this game is the same as this game except a relabeling of agents. So at this history, if delta is less than 1 over 2, what will player 2 do? Play? Stop. What about this subgame? Well, this is the same as the original game. So because of what we have observed here, what would player 1 do? Stop. 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 So conclusion, if delta is less than 1 over 2, what do you expect? What? Delta is less than 1 over 2, then subgame perfect Nash solution of the game gamma will be the strategy profile. Okay, so that's a profile which consists of player 1's actions, A1, well, let me use A1t, t from 1 to infinity, A2t, t from 1 to infinity, where for any t in, for any natural number t, A1t is equal to A2t and that's equal to S. Okay? Okay, so far so good? I forgot to close the bracket here. That's a profile consisting of a strategy of player 1 and a strategy of player 2. Or you could have just simply written S t from 1 to infinity, S t from 1 to infinity. Oops, yeah. Okay? Okay? So far, so good? Any questions? Okay, so now let's see what happens. So when delta was less than 1 over 2, then else become very easy. Okay? By the way, I would ask you to think about Nash solutions of this game. Okay? Not finding all the Nash solutions, but try to find, if it exists, try to find a Nash solution which is different than the subgame perfect Nash solution. If there is no such Nash solution different than the subgame, well, we already know that this is also a Nash solution by definition. Okay? But try to, if there is a Nash solution which is different than the subgame perfect Nash solution, try to find one. Otherwise, try to show that there is none. Okay? Just like we did for Stackelberg. So what happens when delta is bigger or equal to 1 over 2? What happens if delta is bigger or equal to 1 over 2? So your claim is the subgame perfect Nash solution would be such that player 1 starts with S, all continue. Okay. Right? What about player 2? That's not a profile yet. By the way, there's no, this is not good because it looks like there's a last action. That's bad notation. For now, I'll just write it like this. Okay? Don't put a C at the end. If you want to put a C, put it in between, and then more dots. That's for player 1. For player 2, what does he start with? What action does he take here? Continue. And then the rest? Well, there could be the same game, but there could be maybe more than one subgame perfect Nash solution, which they mix. So maybe, well, let your friend finish. What do you want the rest to be? See, it doesn't matter. Anything goes. Okay. So to satisfy your friend, would it be okay if I put an S here? Okay, so if I put an S here, player 1. Okay, well, wait a minute. So actually, so your friend has a point. So for now, let's assume that delta is bigger than 1 over 2. Okay? So can I put a stop here? No, right? If delta is greater than 1 over 2, so for this strategy profile to be a subgame perfect Nash solution of this game, it has to be a Nash solution of this game. So S1 should be a best response to S2. So if player 2 is going to play stop at this history, then player 1 If he says stop, his payoff is going to be 1. If he says go, his payoff is going to be 2 times delta. And if delta is greater than 1 over 2, this animal is going to be bigger than 1. So in that case, he would not play stop here, but he would play go. So this strategy is not a best response to this strategy. Okay? So maybe I should put a continue here. Right? Still uncomfortable? So the first part is okay. You're right. You see, the condition was if this was a subgame perfect Nash solution, the restriction of this profile to this subgame, the subgame where player 2 starts, should also be a Nash solution. That is, if I cut this part, I'm sorry, not that. So if I start from here, it means that I remove this and keep everything else there. This profile should be a Nash solution of this game. Is it?
So they should alternate.
Sorry?
They should alternate.
Okay, but first of all, do you see that this is not a subgame perfect Nash solution of this game? Okay. So there's a problem. So your friend suggests they should alternate. So how do we alternate? Let's try. You try these things. So S1. Start with SC. SC. So I'm sorry. We're writing a strategy, not strategy set. That's small. Player 2? C, S, C, S, C. I should use the same thing here. S, C. Okay. Everybody satisfied? Bless you. You're not happy? What's the problem?
For example,
So you mean second subgame, this subgame. So,
if I'm player 2, I know the player 1 will continue. So I should stop.
oh, by the way, I've messed up the symbols. I wrote G here, C there. What did I do before? C, so I'm sorry about that. I keep thinking about, yeah. So, sorry, I cut your, so if,
I know player 1 will continue next. My maximum payoff will be delta cube 1, which is less than delta 1, so I should stop with that one.
let's stop that. So again, what your friend is doing is, so restrict your attention to this subgame, which means that erase this, okay? So what happens, he continues, and then player 1 continues, okay? And then the maximum payoff from this point on that player 2 can expect is going to be delta cube, which is, if he played stop, his payoff was going to be delta. Delta cube, because delta is less than 1, is going to be worse. Yep. Player 1 always plays stop. Player 2 always plays continue. Everybody agree? Sorry? You agree? Okay, well, let's check. Okay. Let me redraw this. got messy. So stop, I'll use continue. Now go. 1, 2. Stop, continue. 2, 1, delta, delta. Player 1, stop, continue. 1, 2, delta square, delta square. Player 2, stop, continue. 2, 1, delta cube, delta cube. So the beginner always says stop, and follower, the second player, always says continue. Okay? So if that's the case, the payoff is 1, 2. So let's check. Okay? So if player 2 is playing this strategy, what is the maximum payoff that player 2 can expect when he says continue?
2 delta square.
Well, actually, sorry, 2?
When player 2 plays continue, maximum payoff we can expect is 2 delta square.
It's
Player 2.
for, no, I'm asking about player 1. The payoff that player 1 can expect. So player 2 always plays continue. Given this, we're looking for our best response.
Delta square is the maximum payoff we can get.
So here, if he says stop, it's going to be delta square. If he says stop here, it's going to be delta to the power 1. So his payoff is going to be delta. The maximum he can get is delta square. If he says stop initially, his payoff is 1. So what does that mean? Saying stop at this node is a best response to this strategy of player 2. Okay? And because that's the case, so that will be the case for any subgame in which player 1 starts because of the symmetry in the game, right? So now let's check for player 2. Given the strategy of player 1, is this a best response? So we'll look at from here. If he says continue, player 2 is going to say stop. His payoff is going to be delta 2 square. If he says stop, his payoff is going to be delta. So what do we know about the relation between delta and delta square 2? And what did we have? We had delta bigger than 1 over 2, delta square. So it is a best response for player 2 to say continue, right? Okay. So far, so good? Not? What do you mean by not always? So at some node, it would be something different. Well, for example, where? Sorry? Well, as long as delta is bigger than 1 over 2, we have this, right? So delta cannot be, we already analyzed the case when delta is less than 1 over 2. It was to play stop always. When delta is bigger than 1 over 2, that's what we have. Okay. Okay. Of course, what this shows is that this pair, okay. By the way, by doing this analysis for this subgame, we actually automatically do it for every subgame. Okay. Remember, for subgame perfectness, we need it to hold for every subgame. Okay. Actually, that's why we have all the C's in this part and all the S's in this part. Okay? So far, so good? So, this pair is a subgame perfect Nash solution when delta is bigger than 1 over 2. So what is the question that we should ask now? That's one question. What else? Well, every subgame perfect Nash is a Nash. Sorry? Is this the only one? We've tried several other. They didn't work, but that doesn't mean that there's nothing else. So you have to show that there is no other. Okay? Yep. Player one always says continue, always says stop. Okay. So actually, we're kind of running out of time. I'll leave those as for you to think. Your friend's claim is okay. Your friend's claim is that this is also a subgame perfect Nash solution. Okay. I'll leave this, and I want you to think about the case when delta is equal to 1 over 2. I'll leave those as an exercise for you to think about it. Okay. Now I want to introduce another game because we're running out of time. So think about it, and if time allows, Thursday we'll talk about it again. But I would prefer it if you really think about it. Okay. So, but the moral of the story is, if you have an infinite horizon game and you're looking for subgame perfectness, one of the things, this doesn't always work, but check if subgames are identical, well, in a more mathematical term, is isomorphic to the original game. If that's the case, you have a strong tool under your hand. Okay? But that's not always the case. Okay? And when that's not always the when you have a game when that's not the case, and if it's an infinite horizon, well, you're kind of in a problem. Those games are not that easy to solve. Okay? But before we call it a day, I want to introduce another game. In 204, have you studied alternating offers bargaining game? Yes? Yeah. Well, anyhow, has everybody? No, not everybody. Of course, the engineers didn't take 204. So let me still. So we have two agents who have produced 1 unit of a good. The problem is how to share it. The method that they use is, first, one of the players, let's say player 1, makes an offer on how they should share it. Okay? So he tells that he should get x1 units of it, or, the good is a homogeneous good of unit length, okay, of 1 unit. So if he gets x1 unit of it, 1 minus x1 unit is left to the other agent, okay? Okay. So then player 2 can accept this offer. If he accepts, player 1 will get x1 units, and player 2 will get 1 minus x2 units. If player 2 rejects this offer, he makes a counteroffer saying that you should get y1 units, and hence I will get 1 minus y1 units. Then player 2 can either accept or reject. If he accepts, player 1 gets y1 units, and player 2 gets 1 minus y1 units. If he rejects, then player 1 makes an offer, and the game continues in this manner, okay? So, because once we know how much agent 1 is getting, we automatically know how much agent 2 is getting. I'm going to write the actions of players in terms of how much they are offering to player 1, okay? So rather than, so I will say the set of actions for player 1 is to choose a number between 0 and 1. And the action that he chooses is what he would like to get himself, okay? So when you see the x1 here, you should understand that player 1 is getting x1 units, and hence player 2 is getting 1 minus x1. And once player 1 makes an announcement, it's player 2's turn. He can accept or reject the offer. If he accepts, the game ends. Player 1 gets x1 units, player 2 gets 1 minus x1 units. If player 2 rejects, now it's player 2's turn. He makes an offer on how much player 1 should get. So I'll denote that with y. Let me call it x2, okay? And then player 1 can accept or reject the offer. Actually, let me erase this and try to draw it here. I need more space. Okay, so the offer x1 was accepted. Player 1 gets x1 units. Player 2 gets 1 minus x1 units. So that's a terminal history, terminal node. Offer of x2 was accepted. So player 1 gets x2 units. Player 1 gets x2 units. Player 2 gets 1 minus x2 units. Okay, again, here player 2 accepts or rejects. If he accepts, player 1, I'm getting tired. That's player 1 gets x3 units. Player 2 gets 1 minus x3 units. And the game continues. Okay. Now, the thing is, with each counteroffer, time passes. Here, this is the first period, t equals to 1. The second period, t equals to 2. The third period, t equals to 3. So getting x1 units in the first period is not the same as getting x1 units in the second period. Okay? So as time passes, as the bargaining, as the offers keep being made, time passes, and hence the players become less happy from getting the good, okay? So the way we will introduce that is we'll multiply the amount, the payoff, so he gets x2. His payoff is going to be delta x2 if he gets it in the second period. It's going to be delta square x3 if he gets it in the third period, and so on. Actually, so players will discount future utilities at the rate of delta, okay? Actually, let's assume that they discount at different rates. Yep? Yeah, I'm going to do, so they'll discount at different rates, so we'll assume that player 1 discounts at the rate of delta 1, And the same thing is true for, as your friend noted, player 2. So he discounts at a rate of delta 2 square, and so on. Okay? So that's a game. Again, it's an infinite horizon game. Okay? So the question is, does this game have a subgame perfect Nash solution? And if it does, what is the set of subgame perfect Nash solutions of this game? So, by the way, our time, initially I was planning on doing it, but our time is a bit restricted. I would recommend that you try to solve it for finite horizons. So assume that the game ends in 2 periods. So, but then this becomes a terminal node. You have to assign a payoff. Assume that in this case, player 1 made the offer, it was rejected. Player 2 made an offer, it was rejected by player 1, and the game ended, the bargaining ended. So that's a terminal node, hence we have to assign a payoff to it. Assume that if the game ends with disagreement by both parties, the payoffs are 0, 0. Okay? Try to find the subgame perfect Nash solutions of the finite horizon version of it. When, say, the game lasts 2 periods, and when the game lasts for 3 periods, and try to find the general formula when the game lasts k periods. Okay? When it's a finite horizon, although it's an infinite game, this is not a finite game because there's infinitely many nodes. This is not a finite game, but it's a finite horizon game. Hence, you can use backward induction. Okay? So if it's a finite horizon game, you can use backward induction. Sometimes it's easy to use, sometimes it's not. Okay? I almost forgot. Okay? So we don't have enough time to do that, but I do recommend that you think about it, and next lecture, if you bring your answers, I would be happy to discuss about it, because I would like to relate that with this. Okay. So, what to do? So let me call this game Gamma 1, the game in which the alternating offers game, the infinite horizon alternating offers bargaining game, in which player 1 starts by making an offer. I'll denote that with Gamma 1. The infinite horizon alternating offers bargaining game, in which player 2 starts with Gamma 2. So, what are the things that you notice? Again, because it's infinite horizon, we cannot use backward induction. There's no last game. There's no smallest game, subgame. But again, what do you notice? Actually, this game and any of its subgames are isomorphic. They are, in a way, identical up to a renaming. Okay? Well, this game and this subgame are exactly the same. They have the same preference relations. Numeric representation might be different, but they have the same preference relation. This game and this subgame are identical up to a renaming of the agents. Okay? So just like the previous game, that's something that we can do. Okay? So, how to take care of that? How to use those properties? What would you do? Given that you handled this in 204, you should be able to give me some idea.
By introducing the one-shot deviation principle.
Okay. Okay. So there's a property called the one-shot deviation principle. At this moment, we don't know it. so we won't be able to use it for now. But maybe next lecture we'll get into that too. So, well, again, yep.
For example, we can introduce two notations, the minimum and the maximum that each player can get.
Mm-hmm.
We can use that to define like, if the minimum is greater or equal to
Uh-huh. So that's a good idea. Actually, we used similar ideas in the previous case. So I don't want to draw the whole thing, but rather than this being the first period, let's say that this is the t period. So, and this is the period t plus 1. Okay? But this game, this subgame is identical to gamma 1. This subgame is identical to gamma 2, which is identical to gamma 1 up to a renaming. So now, when player 2 rejects, he would know that they will be playing the game gamma 2, and they will be playing the subgame perfect Nash solution of this game if it exists. We do not know whether it exists or not. But we'll do a trick, which we sometimes do in mathematics and economics. We say, well, let's assume that it exists. And then using that assumption, we try to figure out what it looks like. So if it had existed, what would it be like? Okay, so assume subgame perfect Nash solutions of gamma 1, hence of gamma 2, because those are, again, identical games, is non-empty. Is non-empty. Okay. So, well,
And we know that each player on their proposed the same.
they proposed a
Because we know that if the subgame perfect hash exists, then when we take from each history, then it is also a Nash solution of the.
it will be the same. But again, you know, there could be more than one subgame perfect Nash solutions, and so we have to be careful. Okay? So if, you know, it could be that he makes a certain offer at odd periods and another offer at even periods, okay? Which would also mean that he makes similar offers at even periods, and he makes the offers that in even periods, he makes the offers that he did make in the odd periods and the other strategy, and vice versa. Okay? So it doesn't mean that we can't automatically say that because of this identical, you know, the structure, he will be playing the same thing at every history. We can't automatically say before. So if player 2 rejects the offer, what can he expect? Well, then they will be playing the game gamma 2. And we assume that, well, this also implies that subgame perfect Nash solutions of gamma 2 is also non-empty, okay, because they're identical up to a renaming, okay. So if he rejects, the rest of the game will be played according to a subgame perfect Nash solution. And hence, the maximum payoff he can expect is the maximum payoff he can get at any subgame perfect Nash solution of that game. And the minimum that he can expect at any subgame perfect Nash solution. So let me introduce some notation for that. Let's use capital M2. Okay. Superscript 2 to denote the agent that we're talking about. Subscript 2 to denote the agent that we're talking about. Superscript 2 to denote the game, the agent who starts playing in that game, the subgame, okay? So I'll write this. Don't write yet. So that's going to be maximum of U2 of S1, S2, where S1, S2 is a subgame perfect Nash solution of the game gamma 2. Okay? So far? So good? Okay? So this 2 denotes that 2, and that's the agent. Of course, there's a problem here when I write this maximum. This is a set of, we assume that this set is non-empty, so we do have a set of numbers here. But this set of numbers might not have a maximum. Okay. Do you see? So what is the maximum of this set of numbers? What is the maximum number? What is the maximum x which is in this set? There is no such number, right? Okay, this set doesn't have a maximum. This one does, it's 1. Okay, so the maximum doesn't exist, but the supremum, how many of, anybody who doesn't know about the supremum? Okay, more than, well, we have 2 minutes. For now, take it like the maximum of a set. I'll send you the proper definitions, okay? Take it like the maximum. So actually, most people will just write maximum here, but you have to be careful. If the set is not, the maximum might not exist. In that case, we take the supremum, but think about this as, and let me give you one more definition because we're running out of time. Small 2, this I'm going to write the minimum payoff that player 2 can get in this game. Again, the minimum might not exist, so I was thinking that most of you would know supremum and infimum. So think about them as maximum or minimum, but for mathematically inclined people, it's not minimum, it's infimum, okay? But for now, think of this as minimum, think of this as maximum. But for those who are mathematically inclined, the correct way of writing is supremum, infimum. But for our purposes, at least for today, let's take maximum. Okay? So, before we stop, what would player 2 do? For sure, what can we say? If the offer that he has received is less than small m22, what will he do? He would reject, right? Because by rejecting, he would guarantee at least this much, okay? So, and if the offer that he receives is more than m22, that is the share that player 1 gives to player 2 is bigger than m22, what will he do? He would accept, okay? So, yep.
I think he would accept delta 2 times m2, not m2, because in the next stage you might get m2, the maximum, that is discounted in the next
Okay,
stage.
okay. So that's the other part, okay? So player 2, when we're comparing, it's about getting the amount, let me call this y1 for now, okay? He's going to compare getting y1 today and getting a number between these two in what we call the continuation game, okay? That is the maximum payoff he's going to be getting when this game plays. And as your friend suggested, what should we do? Multiply them with the discount factor of player 2 because he's getting Y1 today, but he's guaranteed to get something in between sometime later, the earliest tomorrow. Okay? Okay? So, what we should do is, we're going to stop now, but think about this. Because the rest of the game is going to be the rest of the analysis is going to get a bit complicated. So if you come next lecture, on Thursday's lecture, thinking about this, it will make things faster. Given this behavior of the second player, what would player 1 do? Remember, player 2 compares accepting Y1, the offer made by player 1 today, or getting something in between these two numbers in the continuation game. Okay? Given this, what would player 1 offer? What is the best thing for player 1 to do? Okay? Think about this. Unfortunately, we have to stop here. So